Welcome back, ladies and gentlemen. In this short video, I'm going to do problems number 37 and 38 on page 265 in your textbook to help you prepare for practice E homework. Now, before you do this, I really hope you'll watch those videos that I recommend so that you understand the basics of torque, because that would really make a difference for you to understand how to apply the equation. All right, so let's read the first one. A bucket filled with water has a mass of 54 kilograms and is hanging from a rope that's wound around a 0.05 meter radius stationary cylinder. If the cylinder does not rotate and the bucket hangs straight down, what's the magnitude of the torque the bucket produces around the center of the cylinder? So yes, I recommend you doing a picture, and you don't have to be an artist, as you can see mine. All right, so here's my picture of my bucket of water. Not a very nice bucket. And here's the rope that it's hanging on. So you're gonna have to picture that this rod is sticking straight out, and the rope is around that rod. And they tell you the radial distance to the bucket is 0.05 meters. And I went ahead and just drew a circle for the center of mass. So we're gonna pretend that that whole bucket of water mass is just a dot, and that's where my distance is till, for 54 kilograms. And they want to know what the torque is. So what's the equation for torque? Well, hopefully you saw, we use the letter tau, that's lowercase t in the Greek alphabet, tau. Force times the distance times the sine of the angle. When it's exactly 90 degrees, which it is here to this rod that's sticking straight out. When I put my hand there, you can't really see my pen standing straight up. Exactly 90 degrees. The sine of 90 is 1. So this goes to 1. Now, sometimes you'll see this as F times R for the radial distance. Why? Well, because when I start swinging it, it can go this way, it can go this way, and you can see that it can swing around and around, and hence that's the radius. Okay. All right. So what is my force? Well, my force has to be the force due to gravity, because you know that anything has a force due to gravity. Pointing straight down, and that's mg. Okay, so the force is mg times the distance. So let's just do that. mg here times the distance. All right, I forgot to turn off this light. See if you can see better. Okay, so we have 54 kilograms times 9.81 meters per second squared. That gives you your newtons times the distance, 0.05 meters. So we've got 2 significant figures and then 3 significant figures. So what do we have here? That's why I turned the light on. I can't see. 54 times 9.81 times 0.05, and we get Newton meters, 26.487. So 26.487 Newton meters for torque. That's our T, the little hook there. And so 2 significant figures, well, I guess I have to say it's about 26 Newton meters. All right, so this was just showing an application of our equation for torque. All right, let's look at the next one, number 38. I'll zoom it in here. 38. The mechanic jacks up a car to an angle of 8 degrees with the horizontal in order to change the front tires. You might do that. The car is 3.05 meters long and has a mass of 1130 kilograms. Gravitational force acts at the center of mass, which is located 1.12 meters from the front end. The rear wheels are 0.4 meters from the back end. Calculate the torque, here it is, the torque exerted by the car around the back wheels. So we got to pretend that the hinge, kind of like the door spinning when you push open the door open, the hinges is where it's spinning around. It could go all the way around. And here we're talking about where's the torque with respect to the back wheel. So yes, you have to draw a picture. So let's see my picture. Oh, let me unzoom. Here we go. Maybe too much, huh? Okay, so there's my picture. Now, what is it, the information they gave us? I have to map it up to our picture here. The first thing they tell you is, well, it's 8 degrees up, but it's 3.05 meters long. So there it is. I drew 3.05 meters long. Then it tells you that it has a mass of 1130 kilograms. I wrote that down also. Then it has the center of mass is 1.12 meters from the front end. Why would the center of mass be towards the front? Probably because the engine and all the heavier stuff is in the front. So instead of being in the geometric center, it's not. So center of mass is at this point here, and it says it's 1.12 meters from the front of the car. So I write 1.12. I'm extending little lines to show where that center of mass is. That's why I drew that one there. And then it says it wants the rear wheels are 0.4 from the back end. So I draw that too, 0.4 from the back end. All right. So we need to know, here's our equation. And by the way, here it is when it's lifted up 8 degrees. This is my front end, and here's my back end. So we know the equation is mg, again, because this guy is, mg is going straight down to the earth, that's the force, times the distance, times the sine of theta. Now here's what's interesting. This is where I'm hinging up. Oh, good, this time you can see my pen. I'm hinging it from here. So I need the angle with respect to here, not this angle. Okay, so no problem. No problem. I know that if this is 8 degrees here, then my angle from here to here must be 90 minus 8. So this must be 82 degrees. 82 degrees, because everything's hinging from here. All right, so I know that my angle is 82 degrees. My force F of G is just going to be m times g. Now, what's the distance? Now, the distance has to be from that center of mass to the line of where the tires is. Again, here is where my hinge point is. So along this line here, I need this distance, but they didn't give us that distance. They gave us a whole bunch of other distances. They gave us 3.05 from end to end. They gave us from D to the front end is 1.12. And then they gave us from D to the back end is 0.4. You look at the picture and hopefully you can realize that 1.12 plus D plus 0.4 is equal to 3.05. So I just have to add these two up and subtract it from 3.05 to figure out the D. Or however you want to figure that out. You can say 1.12, oh, I need something underneath it. Sorry, there we go. You can say 1.12 plus D plus 0.4 is equal to 3.05. You do that. Okay, so then D is equal to 3.05 minus, I guess we can do each of them separately, minus 1.12 minus 0.4. That works too. I was going to add them up and then subtract them, but they're all correct ways of doing it. So let's figure out what D is. All right. That was from before. All right, here we go. 3.05 minus 1.12 minus 0.4. And I get 1.53 meters. 1.53 meters. All right, now I'm ready to plug stuff in. So let me rewrite it over here. Tau, what's FG? Let's see, it's mg. This part here is mg. And that was 1130 kilograms. 1130 kilograms times 9.81 meters per second squared. That gives me my newtons. Here's my distance, 1.53 meters. Now I have Newton meters, but I have to do the sine of the angle. Remember, sine of the angle tells you you just want the perpendicular distance from the force to the hinge point. All right, here we go. Times the sine of 82. Okay, let's plug that in. All right, I'll leave the 1.53 there. I'll leave that there. Times 1130 times 9.81 times the sine of 82. I think that was right, 82, yeah. And I get 16795, here we go, what is it? 16795.45 Newton meters. All right, so what is that really? That's 16,795.45 Newton meters. Yes, it's appropriate since we have to worry about significant figures. We can do scientific notation. So what would that be? 1.67 Oh, 1.67. That would be actually 1.8, huh? Because you can't put 7. It should be 8 times 10 to the, let's see, what would that be? 4 Newton meters. Okay. All right. So again, what do we have to do? We had to figure out the torque was the force times the distance times the sine of theta. And in this case, yeah, it was 8 degrees raised, but I needed from the axis of perpendicular to the rotation point, the center of rotation. Okay, and that was 82 degrees. And then I just plugged in mg times that distance times the angle. And that's all we have. And again, I really recommend that you be sure to check out those videos that I recorded. All right, see you next time.